Okay, good afternoon, everyone. My name is Michael Tsai. I'm from Department of Computer Science, Information Engineering at National Taiwan University. So now I'm going to talk a little bit different from the previous topic. I'm going to talk about more of the application and networking aspect. So the topic of my presentation today is performance evaluation of CDMA-based wireless sensor networks with long-thing topologies. So this is joint work with my master's student, Ming-Wei, and myself. So let's talk a little bit about motivation first. So if you look at today's deployment of wireless sensor network in real world, and you're going to see that most of them exhibit, probably not most of them, a lot of them exhibit a special type of topology. So if you look at this picture, this wireless sensor network basically monitors the tension level of each steel cable in this bridge, and try to warn you if there's anything abnormal happening. And if you look at the deployment of the sensor nodes in this, sorry about that, since the laser doesn't really work. So if you look at the sensor nodes over there marked as C21, C22, they basically form a long line, or you can say it forms a long single chain. And on one side of the chain, you have the gateway. Basically, you have all the sensor nodes collecting the sensor data and try to forward toward the other end of the chain. And eventually, the gateway will be able to collect all the sensor data and forward it to, say, a server inside the cloud for further processing. And another example, this is basically an interior map of a mine. And if you think about trying to deploy a wireless sensor network within the mine and monitoring for example, the temperature, the gas level, the air quality inside the mine, try to ensure the safety for the miners, then obviously the shape of the network or the topology of the nodes are going to be long thing. Again, there are multiple branches within inside the mine, and if you look at each of the branch, is basically a single line, single chain. And say if there's an explosion happening within the mine, then what you want to do is basically try to allow each sensor to increase their sampling rate, because you want to know what really happens within the mine. And you want to make sure that, for example, if you look at the recent event of the mining accident in Chile, say if we have wireless sensor network installed in this mine, then obviously it will be easier for you to understand what's happening within the mine. So the key point here is most of the wireless sensor network are designed to conserve energy. So you use, for example, TDMA as a MAC protocol for wireless sensor network. But in this emergency kind of event, you want to switch to a different mode, because now energy consumption is probably not a concern right now. You want to know more about the environment. You want to increase the sampling rate. Hence, from the network perspective, what you want to do is really to increase the throughput. And that's really where this work is coming from. We want to make sure that we use a different kind of protocol that allows us to increase the throughput. And that's where we take CDMA into consideration. So let's look a little bit about what's the scheduling model for TDMA and CDMA. So if you look at TDMA, basically what happens is like this. B is transmitting to A, and C cannot transmit to B at the same time, obviously, because the nodes, wireless transmission node is usually only half doublets. You cannot transmit and receive at the same time. So C cannot transmit to B. Can D transmit to C? No, because wireless communication is always a broadcast. So B is going to have an interference to C while D is transmitting at the same time. And because in TDMA, all the nodes are using the same PN code, using the same kind of code, you can think of it as speaking a same kind of language. So there's no way for C to distinguish the transmission from different nodes at the same time. So finally, E can transmit to D at the same time that D is transmitting to A. But now, nodes that are 3 hops away from each other can transmit at the same time. So which means the duty cycle of this type of system is only 1/3. So only one out of all the one out of three links are transmitting at the same time. But if you switch to use CDMA, now this is still the same. C cannot transmit to B at the same time. But now, because D is using a different kind of code transmitting to C, so B is using one kind of code, D is using a different kind of code transmitting to C, although there's still interference from B because now they're using different kind of code, C will be able to distinguish between transmissions from different nodes. And if you look at duty cycle, now nodes that are 2 hops away from each other can transmit at the same time. So that means the duty cycle for this type of network is now 1 half. So this is really where the performance difference of TDMA and CDMA is coming from, and we're going to see that in a couple of slides. So another motivation for this work is really that we recently found a type of radio chip, off-the-shelf radio chip that can do CDMA. So traditionally, CDMA is only for use in cellular network, but not for water sensor network. Only theoretical work can be found in existing literature. So we found this type of radio which can do spreading communication, spread spectrum communication. But most unique feature of this radio is that the spreading code, or the PN code, is configurable. So you can basically write to the register of this radio and be able to configure what kind of a spreading code you want to use. And also for this particular module that we found, can do RSSI measurement as well as doing very fine level of power control. And all those are very important for us to use it to implement a CDMA network. But this work actually is a pilot study of a larger project. Basically, we're trying to utilize this radio to implement testbed, but this is basically a pilot theoretical study to understand how much improvement can we have if we use CDMA instead of TDMA. So let's look a little bit more. If you look at CDMA, again, CDMA is each node uses a unique transmitting PN code, while in TDMA, for example, if you use AO2.15.4 to implement TDMA, then all the nodes will be using the same set of PN code, the spreading code. And also, inside TDMA, you usually need some kind of time synchronization to make sure that all the nodes have a common time reference. And that actually is bad for the performance in the network in some sense, because all the nodes, while they are three hops apart, but if they transmit at the same time, the interference will look very much similar to each other. In other words, the cross-polation or the interference will be larger. And if you're using CDMA, basically you don't have the requirement of having a very accurate time synchronization. So you don't have that kind of problem. So now, let's look at what we're trying to evaluate. So basically, we assume that transmission power is adjustable with continuous level, and it has a dynamic range of about 25 dB. And we try 3 different kinds of approaches. In the first kind of approach, we use full power allocation. So all the nodes are transmitting at the maximum transmission power. A different kind of a power control algorithm based on literature we found. And the idea is to make sure that all the signal quality level are the same. And we gradually increase that and see what can we achieve. And we calculate what's the power allocation for all the nodes within the chain. And the downside of this algorithm is that it needs the accurate path loss information between any 2 nodes within the chain to calculate what is the power allocation for all the nodes. And the third kind is the one that we found, or the one we proposed. It's based on the second kind, the result from the second kind. But instead of using a very accurate power allocation, we just do some approximation of the result we found. And we found that has very good performance and also much simpler. So we're going to see the result now. In this slide, basically what I'm showing you, x-axis is the node ID. So node 0 is basically the gateway, and node 30 is toward the other end of the chain. And this is showing the transmission power that we found using the second approach. And you can think of it as the optimal way to allocate the power, transmission power, to sensor nodes. And different curves basically give you results for different path loss exponent. And what we found from this is the power allocation actually looks very much like a single linear line. So although we use very sophisticated algorithm to calculate power allocation using the second approach, but in this kind of environment, actually, it looks very simple. So this is how we do it. So in the heuristic approach, we just use a single line to approximate the power allocation for all the nodes. So in this slide, we're trying to compare the route bit error rate of different kinds of approach. So x-axis represent the number of nodes in this single line of chain, and y-axis is route BER, and that's the error performance you're going to get in the network. So if you compare a different curves, so you're going to see CDMA basically outperforms most of the cases in TDMA. So there are different curves of TDMA, but they represent different level, different accuracy of synchronization. So CDMA is basically, so the lower the better because we're talking about bit error rate. And this is only using a very simple full power allocation scheme. All the nodes are transmitting at the maximum level. And you can see that CDMA already outperforms TDMA in terms of error performance. But instead of looking just at the error performance, what we really care about is the throughput. So now we take the duty cycle, which we just talked about a couple of slides before, into account. And effective throughput is basically you multiply the packet reception rate with the duty cycle. So in this slide, again, we're comparing CDMA and TDMA with different lengths of chain. You can see that CDMA, once you have very good SNR, the signal quality between neighboring nodes are good enough, then you can see that the CDMA is doing almost 50% better than TDMA. Okay, and now if so previous result we look at it, but in a more controlled environment, because we did not consider fading, wireless fading, and that's a very common phenomenon you're going to see when you put the nodes within a building, for example, or within the mine. So in this slide, we're trying to evaluate what is the performance for different kinds of protocols, and if we include fading in the model. So in this slide, the fading model we use is called Raichen, and that's some kind of a model you're going to have if the neighbor nodes have a line of sight path between them, while you have a lot of different scattering signal created by reflections, and that's usually called multipath. So again, we're comparing the performance of CDMA and TDMA, but for CDMA now we're comparing the performance when you're using different kinds of power allocation scheme. So we have full power heuristic we come up with, heuristic scheme we come up with, and also the based on the algorithm we found in the existing literature. So in this slide, you can see CDMA always outperforms TDMA when the number of nodes is more than 10. And so that means CDMA can really do a better job than TDMA. But now we want to increase the throughput further. You're going to see that if we use full power control, then it's the worst of the three when the number of nodes is less than 20. And if you use a more sophisticated power allocation scheme, then you can do a better job when the number of nodes is less than 20. However, when you increase the length of the chain to be more than 20, then the simpler one, the full power one, starts to perform better than the other two. And the reason for that is actually quite counterintuitive, but it's actually quite simple, because in fading environment, the path loss between two nodes keeps changing all the time, and because the algorithm requires the input of that to calculate what is the power allocation for all the nodes, and because it's changing, the calculation is no longer accurate after a certain period of time, and that's why when the number of nodes is a lot, the performance starts to degrade. So what we found from this work is really one, CDMA can improve the throughput by a factor of 1.5, basically increase the throughput by 50% compared to that of CDMA in single chain topology, which we found very common in a lot of deployment. And our heuristic power allocation can further improve the throughput. We found that very simple in real-world implementation, and we don't need it. We don't need to do a passless measurement, which will create a lot of overhead. And finally, we found that CDMA gives the system more flexibility in scheduling. Now you have more nodes can transmitting at the same time. And our future work is to design and implement a real-world testbed based on the radio chip. A bit over time. Sorry about that.